So I want to do solutions of our homeworks. For homework from 5.4 on recursive algorithms. And so the first one was, it wants you to show you all the steps in the recursive modular exponentiation algorithm. So the algorithm 4, that was about modular exponentiation. Okay, and I'm not going to write down the whole thing in code again, but remember what it does was you're trying to calculate this thing. Okay, where this mod m means the remainder by division by m, and then what it does is you apply, so the function what they call m power. Okay, so it's a power. So this is calculated by this function m power b and m. Sorry, no, that's a mess. Made a mess there. B and m. Okay, and so what you do is if n was even, then you calculate. You divide the exponent by 2. B and m stay in this whole procedure. B and m always stay the same, but then you square, because then squaring and dividing by 2 the exponent cancel each other out, and you take then the residue mod m, the remainder by division. If n is odd, you have to adjust a little bit. That's just a technicality, but okay. So we take then this thing. We can still square it, but we have to multiply with an extra copy of b to get the right power, and then again take mod m. Yeah, in the way it's put in the book, they say they calculate this thing, the remainder mod m, and then they're going to multiply and calculate the remainder of mod m again. But that's such a small difference that I don't even care about it. Would make it slightly less bigger numbers, but let's not think too much about that. Okay, so it asks us to do this. So this is I'm going over question number, what was it? 5, right? Question number 5. And it wants us to do this with 3 to the power 11 mod 5. Okay. So, okay, let's call this routine. Okay, and then, of course, I have to say what happens. There's an initial start, of course, and what is that? That's, of course, important because we need to know when our algorithm stops and what the value is then when it stops. So that is, we have if n is 0, then the answer, so m power b 0, m is just 1. Yeah. Okay, 3 to the power 11 mod m. So this means that b is 3 here, m is 5, but these are going to be fixed throughout, so I'm not going to keep repeating them anymore. What is important is n. N is 11. So since it's 11, we will be in case 2. We are in the else part of the algorithm, right? Because n is not 0. And then we calculate this thing. We take n power 3, 11 divided by 2, 11 minus 1 divided by 2. Okay, so we use this part, and that is 5. 5, square it, multiply it with 3, and then take the mod 5. Okay. Now, of course, we cannot calculate this because we don't know yet what this is. So we do it again, but now n is 5. We are again in the odd case, so what we're calculating is always this. The answer is always going to be the same thing, right? So what we have to calculate now is m power. Well, no, that's not true. I shouldn't write it that way. The next one is, sorry. Okay, so these two, of course, are equal. But now I'm calculating m power 3, 5, 5, and that is equal to, again, we do the same thing. We take m power 3, 5 minus 1 is 4 divided by 2, that's 2, 5. And we take it, because it's odd, we have to multiply still with 3, times 3, and then we mod 5 it. Okay? But again, this we don't know, so now n is 2. We are in the even case, so we do m power sorry, this had to be squared. And then we do m power 3, 1, 5. That is m power, m power 3, 2, 5. That is m power 3. Now, this is the step, right? Here we divide by 2. That's 1, 5 squared times, not times 3 now, not 5. And, right, and so this, it might, in some sense, the algorithm could have also implemented what happens in case n equals 1. It would make it quicker somehow, but it is not necessary. So let's just do what happens in case n equals 1. You'll see it does give it an answer. So 3, 1, 5. Because of course, if you take the power 1, you just have b, right? You could have said if n, so you could have added here in this clause, if n is 0, then this. If n is 1, then m power of b1m is just b. Okay, or b mod m. But okay, this is not necessary because we are in the odd case, so we are doing this step here. And notice that the exponent, this now becomes 0. And so this is where basically, so m power of 3, 0, 5 squared times 3 mod 5. And now we're ready to plug in. So I'm going to start doing this in a different color. So what do I know? Well, this one, if I run the algorithm one more time, it will get me in the initial condition, and so it will tell me this is actually 1. Now, squaring that doesn't do anything, so I find that this is actually 3 mod 5. So, okay, this means that I can go plug this in here. Okay, so this would now be 9 mod 5, which we have to each time take the residual mod of 5, right? Because otherwise the numbers are going to get too big. So we get 4. One way of taking residual mod 5, I remind you, is, of course, there's a standard forward way. You can use a calculator. Many calculators allow you to do that, but in small numbers, it just keeps subtracting the 5 here until you are small enough. Okay. Okay. So you'll see it in the next step that we'll do it. So okay, I know now that this is 4, and I can plug this in here. So this will 4 squared times 3 mod 5. So that is 16 times 3 mod 5. So here is what in the textbook they say, let's take already from this number, see it's already bigger than 5, let's take the residue. It makes it easier in our calculation. Okay, but you could also calculate this whole thing, that would be 48, and then take the residue mod 5. And what is that? Well, you keep subtracting multiples of 5, in other words, you subtract 45, and then you're left with 3. Or, as I said, you can think of 16, you subtract multiples of 5, so 5, that's 11, another 5 is 6, another 5 is 1. So you know that this would be 1 and this would be 3. So the whole thing is 3. Okay, I hope this is 3. So I can now plug this in here, and so this would be 3 times 3 times 3, so 27 mod 5. And that is very easily seen to be 2. I hope that's clear for everybody. Okay, subtract 25, which is a multiple of 5, and then you have 2 left. And that's it, right? Yes, that's it. Yeah, I went through the whole thing. Okay, so that's, then you see how, and how quickly I did this, by the way, right? And even if you would just do this in a calculator, I'm not sure that your calculator, I'll try it with mine here. Oh, I cannot do this with mine. Oh, okay, sorry, I'm not going to try. Problem with my calculator is I have to do, I need a keyboard and I don't have a keyboard on this one. I'm sorry, let me not do it now. I'll figure, we will do it at some other point. Okay. That's one question. The other question was 31. Now, 31, of course, it's a little bit disingenuous that I said 31, right? What actually needs to be done is actually the two previous questions as well, right? So let's see what in 29, so I'm going to do 29, 30, and 31. So 29 said, okay, you start defining a sequence recursively. The first one is A0 is 1, A1 is 2, and then you say that AN is defined as the product now of the previous 2. So this is different from the Fibonacci where you would take the sum, but other than that, it's the same. Okay, so this, and it asks 29 actually asks you to write a recursive algorithm. Okay, and so this is again very straightforward, right? So I'm gonna go here. So the procedure, I'm gonna call it mfib, multiplicative Fibonacci. It's just a, and so the input would be a single number n. Okay, and so we have here two conditions that we initial conditions. So we're gonna do if n is 0, then else if n is 1, then else, and then comes the main definition. Okay, so let me write this up all up. So if n is 0, then return the answer 1. Okay, else if n is 1, sorry, I'm going to write it later, then return 2. Else, and here's then the real thing. Okay, so let me fill in what I said in words but didn't. So if n is 0, then return 1. If n is 1, then return 2. That should have not been in boldface. Okay, then return 2. By the way, this is very cumbersome to do this boldface, so you guys don't have to do that. Okay, you can just write regular thing, or like perhaps caps and something a little bit. But okay, so this takes care of this part. Now, how this one go? Well, this is extremely simple. Mfib of n is simply mfib of n minus 1 times mfib of n minus 2. That is the beauty of these recursive algorithms. They're so very easy to write down. Okay, and that's it. And by the way, this is okay, right? Because our counter, just checking that we didn't violate, that we have a valid algorithm, because this takes, these two steps here take care of the cases n, 0 and 1. So when I'm in this else, n is at least 2, and therefore these two numbers are always defined because they are previously defined numbers, and they are within the range from 0 onwards, right? Okay. So then number 30, I think, asks you to do the same thing, but now, so this is a recursive. This was a recursive algorithm. If you, that's the thing if you do it theoretically, if you don't care too much about calculating these things, or if you're dealing with small numbers. But the iterative, so an iterative algorithm, of course, is slightly more complicated because you're going to have to take care of all the, there's a little bit more playing with the variables and so on. If you remember this from the time. All right, so how does this one goes? So I'm going to call it IFIB, iterative Fibonacci. No, that is not the right word because it's not Fibonacci. I don't know what I call it. I'll call it, okay. So what I'm going to do, I'm going to cheat a little bit, is I'm going to copy this part here. Oh no, sorry, it's this one. Screw this up. What does it open up? Here, copy this image. Okay, that doesn't really work well. Okay, so, but okay, if procedure, okay, I have the procedure, iterative, multiplicative, okay, I have to give some name to it. So here, because the way that we're going to deal with everything is we're going to, so remember what we're going to do. What is this ugly thing? Where does this come from? Why cannot I get rid of that? Okay, whatever. So what I'm going to do is, so let's look at a few of the values, perhaps, just for the fun of it. So we have, we build a series. So this is A0, this is A1, this is A2, A3, A4, A5, let's not go too far. So you have a 1 and a 2 here. Now A2 is the product of the previous two, that is 2. A3 is the product of these previous two, that is 4. So iterative means you do exactly what I'm doing now. You take these two, multiplying together, and 8, and now you change your pair. Instead of the 2, 4, you now go to 4, 8. Okay? And then you do the same thing. Multiply these two, that's 32, and then shift again. So there's two things that we have to do. We start up with the initialization. So we're gonna have, so X and Y are the registers that will, there are these two registers here, right? So if you want, and they will, this little thing is like a little train, moves along, and each time picks up new numbers, and then, okay, I hope you get the picture. So X is 1, Y is 2, the two initial values. And then for I, oh, I guess I have to shoot this again with the, so for I going from, 2, I guess I can put this here. So what is my I? This is the index here. What am I doing? Well, I have to go through, so suppose I'm doing A5, then my I is going to tell me where is my little train here, my little wagon, where is it, right? This is the I position, this would be I is 2, and then the wagon moves here to this part and becomes I is 3 and so on. So I goes from 1 to n minus 1, right? Because the last position that I will be in is here, would be just one less than what I actually want, okay? All right, these are just little technicalities that you should not worry too much about. Sometimes my iPad freezes. What is it doing? Oh, hey, why is it freezing? Close this. Delete. Sorry, my iPad froze. I don't know why I cannot do anything anymore. I can do this. I cannot move. Okay, let me go just this way. So, okay, so I'm going to have to write it again because it seems like I cannot scroll up again. So I did X is 1, Y is 2, and then for I, sorry, to n minus 1, what I'm going to do, well, the new value that I'm going to get, right, so here's X and Y, right, I'm somewhere in the middle of my sequence here, AI, and this is the next one. This element should be the product, so this is going to be Z. X, Y. And now I have to just move this little train there. So this will be the new X and Y, and this is the Z now, right? This is the value Z that we would get. So what does that mean? Well, that Y should be the old X. No, sorry, I have to do X first. Sorry, I'm saying it wrong, right? X is the old Y. The new X is an old Y. I'm saying it wrong, sorry. So the new X is the old Y, and then the new Y is the old Z. And then at the end, we know that Z or Y, it doesn't matter, return Y, give me the answer. So that's the iterative version of it. Okay, so somehow I got control of my iPad again. And then the question really asked is the number 31. That's the question I actually told you to do. Ask you, is the recursive algorithm, which one of the two is more efficient? Okay, so let's say just in calculating A5. So what would this algorithm do? It would has to, as we said, the little train here would make exactly 5 steps. So this is about O of n complexity, because I have to do n steps. If my number that I want to calculate, if I want to calculate the nth number in my row, it basically have to move my little train n times and do this n times, carry out this kind of trickery. But you say, okay, is it then not 3 times n because you're doing 3 operations? Yeah, okay, but remember, O3n is the same as On. Constant factors don't matter. Okay, so it's On. Now what happens here, it's much worse. Like, so imagine what A5 would do. A5 needs to, in A5, here, okay. For A5, I have to first calculate, so if I do mfib5 here, I have to call mfib4 and mfib3. Okay? And then each of these have to be calculated. So mfib4 needs its calculation and mfib3 needs its calculation. And I remind you, although that in the calculation of mfib4 I will use mfib3, I cannot use that because I don't know that. When I'm in one calculation, I'm doing it, and then I go finally said, oh, I found this one, and then I go back to where I was, and then I figured out, oh, I have to do 1, 3 also. Okay, so you see here the way that one represents this often is one makes this in a tree. So you have 5, and for 5 you have to do 4 and 3, and to do 4 you have to do 3 and 2, and to do 3 you have to do 2 and 1, and to do 3 you have to do 2 and 1. Okay, for 2 you have to do 1 and 0, for 2 you have to do 1 and 0, and for 1 you have to do wait, oh, in one is one of the points where I stop, so I don't have to do anything in 1. I was a little bit freaking out because I didn't know what to do, but because I shouldn't have been doing anything. Okay, so let's see how many, and then 2 I still have to do, still have to do 2, right? Because 2 I have to do 1 and 0. So these are the stop nodes. This is in a tree. We'll talk about trees much more later, but I hope it's kind of clear what it is, and the book also talks about trees already. So each of these instances of this calculation, I know what the answer is because that is exactly given by these 2 conditions here. And then I have to build it up, okay? But each node, and so at each node of these 3 nodes, these are this, you know what I mean with this one. I mean this number, so I shouldn't, let me paint this in a different color. So let's do this in green. So to calculate this thing, I would have to multiply the 2 answers that I got here. And then according to this, I multiply the answer that I got here with the answer that I got there, and so on. Okay? And so, for instance, at some point in the calculation, I would also have calculated these 2, and then to calculate this, I would have to multiply the 2 values, not 3 and 2, but the values that I've calculated there, and that gives me the value at this stage. Okay, so, but you see how many calculations do I do? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Sorry, I forgot to make this in a red one because it's the red one. So way much more. And in fact, if you think a little bit about it, it's going to be almost 2 to the 5th, almost 2 to the 4th almost. It's exponential instead of linear that we had here. So this is therefore, this one is much more efficient. This is the efficient one. But you should not think that it means that recursive algorithms are never efficient, because remember, merge sort was extremely efficient, much better than all the other ones, which were not recursive. So it really depends a bit on what type of question you do. And so for recursive, when you have a recursive function, it is so nice and easy to write down the program for it, because it is just copying the original formula. It's just copying this original formula. But the cost is it takes much longer. Okay?